So this is our AP Stats 6.3 video on binomial and geometric random variables. So think about our guiding question as you go. What's the difference between a binomial random variable and a geometric random variable? And how can each be used to determine probabilities of specific outcomes? So remember that binomial random variables count a number of successes and a fixed number of trials. And we look at the likelihood of that happening. So here are some examples of situations, a situation where we'd use binomial random variables in these binomial calculations. So notice that in each of these settings, these four conditions all have to be met for it to be a binomial random variable. And check bins before starting, that's these conditions, before starting any binomial calculation. So just write out BINS. Binary, there can only be two possible outcomes, one classified as success and the other as failure. To show that condition is met, you'd say which one would be success, which would be failure. In the example above, a defective CD or not defective CD. Independent, trials must be independent, so each outcome, the one outcome occurring, a success or failure, shouldn't have any result on any of the other outcomes. There need to be a fixed number of trials. So in the above example, we had 10,000 CDs. You'd say what n is. N is the number of trials. You'd say n equals 10,000. And then success. The probability P of success must be the same on each of those trials. Sometimes the independent part and the probability of success can be the same. So the probability of success changes, and that's showing a lack of independence. Sometimes, like when we looked at the example in class of taking 10 jump shots from different spots on the floor from different distances from the basket. They're independent, but the probability of success changes. So sometimes they are not the same. If you're having trouble with a calculation or looking at a distribution when you're looking at our final or on the AP exam, think, is this a binomial setting, and check that, as they often are. So now I want to give you a more detailed example of a binomial setting. And how we could use these calculations and what we're really talking about. So we're counting x, the number of successes in a binomial setting. And our probability distribution of x would be binomial. And n is the number of trials, p is the probability of success. We'll use the letter k to represent the number of successes we're interested in when we use the calculator. And here's a setting where we could use this. So a star basketball player, he makes about 75% of the shots he's taken in the past. So we'll use that as his probability of success. His team's down by 1 point and he gets fouled shooting a three-pointer as the clock expires, giving him 3 free throw shots. That means if he makes 2 or more, then his team wins. So what's the probability that he makes at least 2 shots? We can represent this with a tree diagram. Recall that a tree diagram has each event. So here's the first shot, success or fail, the second shot, and the third shot. Now these are conditional probabilities along here. This is the conditional probability. Given that he's made the first, the probability that he won't make the second. Over here we have the overall probabilities of the outcomes. So if we wanted to find 3 successes, it'd be 0.75 times 0.75 times 0.75, since they're independent events. And that's given here on the right. Now we want to know, we're interested in the probability that he makes at least 2, but we notice over here there's several outcomes that satisfy that. See that he could make all 3, he could make the first 2 and miss the third, he could make the first and the third missing the second, he could miss the first and make the last 2. So here's our tree diagram representing this process. We would then add those 4 probabilities to get the probability of making at least 2. So about 84% of the time he would make at least 2 of those shots. Now even for 3 shots, a tree diagram becomes time consuming. So what I want you to do is picture these probabilities as tree diagrams when we're going through and calculating them, but also keep in mind, if we were talking about outcomes and probabilities that have more events than 3, the tree diagram becomes even more complex. So we want to be able to use a calculator shortcut to calculate these things for us. And that's where we have to check the conditions. He either makes the shot or misses it. That's the success and fail. Each outcome, taking 1 shot, is independent of the previous. So making or missing one doesn't affect another. N equals 3 here. And our probability of success is 0.75. Calculator shortcut, binomial CDF, found under second vars. If you scroll down once you get to that menu. So you need to have the number of trials n, the probability of success p, and then the number of successes that we're interested in k. Now the thing here is that the calculator will use these values to determine the likelihood of k or less successes, or the probability that x is less than or equal to k. Here we want to know 2 or more. So we have to quickly think, okay, I need to use the complement rule because I know the sum of all my outcomes equals 1 or 100%. So this is that first step. If we want to know a binomial calculation and we're using a greater than or equal to symbol, I want you to write out this first step, which is the complement rule. That the complement of greater than or equal to 2 is less than or equal to 1. And less than or equal to 1 because this is a discrete variable that can only take on whole number values. So this step is key so that you use the right value for k, that we use 1 here. So we use 1 minus binomial CDF, 3, the number of trials, the probability of success, and then the k, the value we're interested in. Because we're using the complement rule, we have to use 1 there, and the common mistake students will make is using 2 there instead. And again, we get about 84%, a bit more exact here because I was rounding off in our tree diagram above. So that's how we use the binomial calculation on the calculator. So go through on your calculator and try to do this now. Your response, it's another similar situation. So I just walked you through an example with the basketball player. Now we're looking at a different situation, playing a board game, and you get an advantage by rolling a sum of 7 on 2 6-sided dice. You have 10 rolls remaining, and you need to roll a 7 on at least 6 of those times. You want to know the probability that you roll at least 6 7s. That means there's at least 6 times where the 2 dice add up to 7. Recall that the probability of rolling a 7 is 6 over 36, or 1/6. So our probability of success there. Use that calculator function that I just used. Think about what is n, p, and k here. And to get full credit, I'd like you to check the conditions for bins, show the work for the complement rule just like I showed it above there, those steps, and say what n, p, and k are equal to in this case, and then write down that probability and interpret it. So pause now and answer the free response question, and then start playing again to get the rest of the video and your multiple choice. One shortcut to find the number of ways, for example, if we were interested in the number of ways that the basketball player could have made exactly 2 shots out of 3, we could use this formula for the binomial coefficient. And this shows us the number of ways of arranging k successes, so k would be 2, among n trials, n would be 3. And this is how it would be by hand. So remember, factorial means 3 times 2 times 1. And then this is the formula by hand. So getting an idea of a shortcut to determine the number of ways. So here we have 5 choose 2, which would be the number way of 2 successes in 5 trials. And there's a shortcut. Keep in mind also, aside before I go into that, that this is not related to 5 divided by 2. Okay, so it's not related to the fraction. It's just a way of expressing k successes in n trials. The Tech Corner on 392 has this on how to do it on your calculator using math and going to PRB. Now, when you do the binomial CDF calculation, it will go ahead and calculate for CDF, it uses less than or equal to. Binomial PDF is what we would use for an equal sign if we wanted to know exactly 2 successes. And what your calculator does is it calculates the binomial coefficient and the probability of 2 and then multiplies those. So the number of ways, for example, if something had a 10% chance of success and there's 3 ways it could happen, 3 times 10%, 30% chance of occurring. So your calculator will do that for you if you use binomial CDF or PDF. So here's just a quick rundown of the calculator functions we've talked about using n, p, and k. PDF for an equal sign, CDF for a less than or equal to sign, and then use that complement rule for a greater than or equal to sign. You need to set up that complement rule step in order to use binomial CDF. Here's mean and standard deviation of the binomial random variable. If that shooter who shoots 75%, if he was taking 4 shots, we'd expect him to make 4 times 0.75 or 3 shots. If you flipped a fair coin 10 times, you'd expect to get 0.5 times 10, 5 heads. In the long run, over many trials, you would get an average of 5 heads or close to it. So that one's pretty straightforward and seems pretty intuitive. Standard deviation, this one's also given to you on the formula sheet, but you need to know that it's for a binomial random variable. So it's the expected value, NP, times the complement of the probability, so 1 minus p, and the square root of all that. This only applies to binomial distributions. And there's one key condition too about sampling without replacement. So if we're taking a simple random sample from a population of size n, capital N, so the sample is little n, the population is big N, we can't sample more than 10% of the population, or the probabilities change so much that we can no longer consider the observations to be independent. Basically, if we take too many from a smaller population, if we sample too much of it, the probability of success changes enough where the binomial calculation breaks down and doesn't give us a good approximation of the true probability. Metric random variables that are very similar to binomial, except for instead of having a fixed number of trials, we're counting the number of trials it takes in order to get one success. So if we're counting until one success, so the number of times that we'd expect until the basketball player makes one shot, then it's a geometric setting. Notice that the conditions are all the same with except of that one where trials. So still needs to be binary, independent. The probability of success needs to remain the same, but now we're counting the number of trials till the first success. And that's a geometric setting. So on page 406, we have a geometric probability on the calculator. It's found in the same place as binomial, CDF, and PDF. GeoPDF is for an equal sign. GeoCDF works the same way for less than or equal to sign, and you have to use the complement rule for greater than or equal to. Now, so take a look at the probability function for geometric on page 406. Value for geometric random variable will do 1 over the probability. So picturing that coin flip, the probability of heads is 0.5. Our expected value would be 1 over 0.5 or 2. That means in the long run, on average, we'd expect it to take about 2 coin flips to get heads when flipping the coin. This question, it's a good time to pause and to read over the summary of 6.3, look through some examples of geometric and binomial random variables. And you're choosing whether this setting is binomial, geometric, or neither, and the appropriate reason why. So pause here to read over the question about the lottery for parking and determine whether this is geometric or binomial and why. Look at those conditions. Bins for binomial, bits for geometric. And here are the possible answer choices for the multiple choice. Determining on your own whether you think it's binomial, geometric, or neither, and the appropriate reason why, go ahead and answer A, B, C, D, or E on your multiple choice form and turn it in.